Good morning. How's everyone? Good. Excellent. When I looked yesterday into my swag bag, I found 3 pens. I thought, wow, how unusual. I love pens, and it's good to see that you can, still get them as conference giveaways. And yeah, these days I guess most people would use styluses and things like that. But just out of interest, because this talk will hook into handwriting and things like that, who's actually taking notes on pen and paper? Oh wow, this is actually impressive. This is like quarter of the room. Um, well, you will have an advantage. Because you actually wire your brain to read handwriting faster and to actually decipher it. This obviously is somehow sorted. Have a look through it. And as a human, you're really good in identifying, hey, these are actually all the same in a row or not. But this is actually what a computer put together. And you see, for example, if you go down here, the 4 and the 9s, yeah, computer thinks it's the same, but you can definitely tell, it's not the same. So we're going to look a little bit into this whole, how do you actually train a computer to recognize handwritten digits. Use Python for that, and a little module called, or a little project called brainstorm. And I give you a little bit of the background, kind of what you need to know for it. I give you a little bit of the stuff we're going to run, so you're going to see a little bit of code. And there's also, that's for the impatient, so you can go and download it now. The actual example, which is very lightweight and I hope easy to follow, because this is really meant as an introductory talk. And it's literally step 1, 2, 3. You run through that. The rest is more or less the craft you need around it, and a few test images if you don't want to scan and prepare your own ones. And this is not a talk about artificial intelligence, deep learning, and all that stuff you read in the press, and where you actually think, okay, yeah, you need to be Google or Facebook or one of these. This is more like the Kiwi Shed version of machine learning. A really well-prepared example, really the basics. If you want to extend it from there, there are many routes to explore. It's really a way to get into it. At some point, you won't get around the math. But right now we won't need very much. You see a little bit, but it's only to illustrate what's going on. So if you think like, oh, you're doing math, it won't be that hard, you don't have to leave the room yet. That's my Uncle Chet, by the way. As you can see, he's outgrown this hobby. So the whole idea comes from biology and especially brain cells. And if you look at it, you have the actual brain, the axon, signals transmitted and whatnot, and scientists thought, okay, we can replicate that, and we create these nodes and we connect them all up. This is almost also where it stops. Your brain is way more complicated than kind of what you can build in a computer kind of easily and on that level, and there are other mechanisms at play. But it's a nice analogy if you think kind of, okay, how does this work? Because it all works in parallel. So it's not that you have like one pass through here and then one pass through there and so on. It's literally that you take kind of the different nodes or neurons. We talk a little bit about how they behave in a moment. They're all connected up and they all interact at the same time. They all fire at the same time. Going back to the idea of a signal, you say, okay, if I have this little node, I have to determine when it actually fires kind of to the next one. So you see one node can have many inputs. Here's 3. It does something and fires to an output. How strong these connections are, you can determine. They're not all equal. Some are stronger links, some are weaker links. And think of it as a weight. How big is your pipe? how much can go through here? Can't be different from this one here. And in here, if you think, okay, everything, all what's coming in is accumulated in the node, at some point it'll tip. Think of it a bucket filling up, and then it pours out, which means it fires kind of to the next one. Or, well, there isn't enough input, it doesn't fire, it doesn't actually go through, and nothing happens. The makeup of these is always the same. If you think of Python writing a class, it's pretty easy to write a little neuron class and then create objects from that, and you connect them all up. There are plenty of examples of that on the net if you really want to go that basic, but it's a lot of work in the end kind of to wire it up and get it right. So what we're going to use is also a framework. And what you have to do when you create kind of these big nets of nodes is actually optimize, because somehow they're all connected kind of with all their signals, and you want to find at the end these points here, kind of at the bottom. Here you have only kind of 2 input parameters, think of that, and later on you can say, okay, we have 3, and each node contributes 1 parameter. So right now, that would be good enough for 3. We will have, in our little example, which is very, very small in the end, 2.4 million. So unless you're living in another dimension, similar to Hitchhiker's Guide to the Galaxy, you know, pan-dimensional beings, it's really hard for us to visualize kind of more dimensions than 3D and plus maybe time. But just think kind of, hey, the whole principle holds. You can do it with many, many dimensions. And calculating that stuff is pretty hard. And luckily, other people thought about that. There are libraries for that stuff around and can use that. You don't have to think about it. It's really standing on the shoulder of giants and just plugging it together and then tweaking it and making it work. Going back to our 3D example, what we're actually trying to do is also find a minimum for us later on when we kind of train. And think of a skier in the mountains. You want to get downhill. It's foggy. You actually can't see where you're going. You only see kind of the vicinity here. Okay, yeah, this direction is going downhill. You go a bit further, you go a bit further, and bit by bit, you zigzag around, you go into the valley, and deeper until you can't go further. And you found a minimum, could be local, could be global, as kind of like illustrated here, because you actually don't know, because you can't look too far. Am I on the here in the minimum in the valley, or am I here in the valley? Also, if you take small steps, it takes a long time. You want to take big steps, but if you take big steps, you can go in the wrong direction. And to balance this all out, needs a bit of experimenting or a bit of experiencing. So we're coming back to that in a moment, and hopefully it'll get clearer then. So, in our case, we are looking at handwritten digits, because it's actually pretty universal. It's been stable for a couple of centuries. Not so much like handwriting. This is actually 130 years ago, and you spot Kiwis will be familiar with Briscoe's, kind of the shop. This is actually the original Briscoe's in Dunedin. And you still can read these numbers. You recognize them. They're not too far. You'll have a much harder time reading this. So we make our life really easy, and we say, okay, we're only going to look at handwritten digits. There are 10 of them, 0 to 9. And we're going to analyze that. For that, we're using brainstorm. It's a library written by a Swiss AI lab, and they open sourced it. It's in Python, and it has a few dependencies. I'm going to talk about that in a moment. It's running on multiple platforms. I got it to work on Ubuntu and Debian. A couple of tips later on that. Windows, much harder. If you have a choice, go with Ubuntu or Debian. Much, much easier, because if you try to spin up the compiler for the math stuff on your Windows box, you have to do a bit of plumbing, and That's not fun, but it works. This is more or less what you have to run in the beginning. Python dev headers, a lot of you will have seen that. That's for building the Python extensions. libhdf5, that's a library for a file system that actually stores matrices and numbers in a very compact and very efficient format, because we're going to store a lot of numbers. And so we're going to use that. And then the last bit, the libopenbls, that is the bit that does the heavy lifting in terms of math and the calculations. Luckily, at this point, we don't have to understand it. We just have to install it, which, as I said, kind of on Windows, is not too easy. I had good success with WinPython. Unfortunately, that's Windows Python 2.7, not under 3. And under Conda, I got it to work under 2.7 and 3.5. These packages, the links are in the slides. They actually help you kind of with the pre-compiled stuff, and you simply have to put it in. So with the last stuff, with the basic linear algebra subprograms, that does the, let's call them calculations, and can do a lot. But it's also optimized for your hardware. And we couldn't run all these calculations on kind of the laptops and desktops you have at home that way without that stuff. It comes back to this whole idea Kiwi Shed. I mean, if you have the facilities and in terms of cloud computing or kind of bigger ones, you can do way more. But here you actually can go far out to calculating a lot of tricky stuff, especially if you have powerful graphics cards, and Brainstorm can enable that you can use the GPU. GPUs on the graphics card are really good with parallel processing. You can leverage that if you really, really want to optimize it. All right, once that's over the line, that's actually after you pull down the example I put up on GitHub. You literally install NumPy, Pillow, and Brainstorm. I walk you through these in a moment. And I found on Debian you also sometimes have to set the environment here. It's kind of one of these things, kind of you just install it, it should work, it should be easy, and kaboom, it blows up. And then turns out, environment variable missing. You find it somewhere on Stack Overflow, things like that, but yeah, here it's kind of like, maybe I save you an hour, or maybe your Google foo is better than mine, but that's kind of like solved that. It's kind of often these little things. So NumPy. That is on top of the BLS that I mentioned, and does the metrics calculations, and really stores nicely arrays that you can handle, slice and dice. Just as an aside, I put this together. If you never touched on it, you really should have a look. Here, NumPy, give me a range 10, which is obviously 0 to 9, and spits that out. And you see kind of it has the, it's a NumPy object, so it gives you kind of the array. And it also tells you with an empty array what it's meant to be. Is it a float, is it integer, and things like that, kind of these little details. You can slice them. You can make them multidimensional. As I mentioned before, kind of the 2D to 3D to 2.4 million D. This can handle it for you. And you can still navigate it. You can do things like reshaping, which will come handy in a moment when we bring it together, because we're going to read in images. And you have kind of the row of pixels, and you actually want to rearrange them, things like that. So you can do operations like much more. Really worthwhile if you haven't touched before and not having a look. Pillow. This is the more or less newish Python image library. This is kind of what we're using to actually read in our little handwritten sample. And somewhere far, far away, we have this little image. The samples are quite small, and I'll tell you in a moment where I got them from. They're only 28 by 28 pixels. And they prepared and roughly look like this. Background is black and just as a simple JPEG. And if you want to get this in, so we can use it for the calculations, you simply go open, reshape it, and load it. So that's NumPy, that's Pillow. Now we need actually the data. This is often with machine learning the hard bit, to get good training data. There is tons of stuff out on the internet in all forms. This is actually one of the most common ones because it's so nicely structured. And it has been used over and over again. Think of it as the hello world machine learning. That's kind of what it's used for. It's 60,000 grayscale images. Originally, they were written by a public servant in a US institute and high school students, I think. And they were separate, and what they actually originally used them for is like, hey, the public servants are the training data, and then we test the high school students. Didn't work very well because the handwriting was quite different. So other researchers actually mixed it up and made this data set out of it. And there are another 10,000 verification on top of that. So actually, if you download it, you get 70,000. 20 by 28 pixels each, and they're normalized, which means kind of from the bigger samples, from the bigger scans they took, they actually made sure, because it might have been blue pen, it might have been red pen, whatever, background always black, digit white. It's a grayscale, so apart from gray values, you have nothing in there. It's 28 by 28 pixels, and the actual digit is kind of like centered or weighted around, so it sits consistently kind of in this 28 by 28 square. A lot of work to prepare. So if you do that stuff with your own data or make your own experiments, you'll discover you're getting sick of Photoshop or ImageMagick pretty soon. But that is kind of a really, really important step to get this to work. All right, step one. Now we're starting to go through a bit through the code. It should be as easy as you run it. It says, please be patient. Goes out to the internet, downloads the packed data set for you, and it creates the HDF5 file, which I said kind of is a nice way of storing it. Because at the end, we kind of want to read the pixel information directly, so it actually packages up for you in the appropriate file format. It doesn't take too long, and that gives us validation data where we actually can test. So our little program won't use this to actually learn what numbers look like. There's never seen it before, so we use that. And we also know what it is. So we not only have the image, with it comes a label, a little description, hey, this is a 3, this is a 4, and this has been verified and tested. And then the actual training data, 60,000 images, which also have the labels, which we pump through the network, and then see, hey, is that right or not, and then correct it accordingly. That you don't do with 60,000 in one go, so we chop it into little batches. In my example, it's 100 at a time. You can choose whatever you like. So how does that now look when you wire it up? This is your prepared image. Ignore that it's blue here. I just thought it's prettier. It is actually black and white. And each pixel you connect to one neuron. 28 by 28, really quickly. 784. Magic. Okay, so we have 784 neurons, 1 per pixel. And each neuron has value 0 to 1. depending on if it's black or gray. And that'll be our input layer. That's how we get actually the stuff into the network. Now, the next layer, we use way more neurons. Gives us more flexibility, and we connect them all up together. So, first neuron from our input layer goes to all of the 1200 neurons, and the 1200 is just, I decided 1200, I could have made 1600. That is again kind of where it comes down to experience. How do you design that stuff? That's where you have to dive a bit deeper and learn kind of what works in what scenarios, because it'll be at the end very specific to our use case. And some stuff works well, and some stuff doesn't work so well. An additional optimization, which I'll talk about later, is that we actually reset 20% to 0. Said, but nah. So on the face of it, we actually mess with our network. So when this is kind of going through, say, okay, I get this information, black, 0, no, don't fire, and so on. 20% of the information gets dropped. This is the input layer. This is our first layer after it, which will be actually not our output layer, because what we want at the end is a classification. We say, hey, is this a 3? Is this a 4? How many classifications can we have? 10. So at the end, we're going to have 10 neurons. So it goes from our input, 784, because that's how many pixels we have. Here, we have also 2 dimensions. You can also think of, hey, what's with video? Well, suddenly you have a time sequence of images, and then you get this as well, which obviously makes your input layer so much bigger already. Again, this is a simple example. But even in this network, if you count all the connections, you end up with 2.4 million. If you're diving into deep learning, things like that, there are many, many of these hidden layers in here. 100, 120. And you run into also problems where they don't behave as you would expect. This is simple enough that you don't have to do anything special in terms of training. You can use always the more or less same type of neurons, things like that, how they react. In more advanced, more complicated examples, you decide actually per layer how they react and how you train them. Maybe you only train part of the network. You preset it differently and so on. But effectively for us, only thing to know is, okay, input layer, output layer, 2 in between, and here we do 50% dropout. We kill that stuff. So that's our design. How does it look now in code and brainstorm? Well, not too bad. Here you create your layers, 28 by 28, because that's how big our picture is, and 1 deep. So for example, if you have here 24 frames of video, maybe that would be 24, 10 out, and the projection is the layer before kind of the output. Classification, you can give it a name, and the naming just makes it easier later on to actually reference it when you actually investigate your network. There's tools and other stuff in there. So instead of remembering some node number and things like that, you give it pretty names. Then we create the network. Layers, input layer. Here's our dropout layer with a 20%. Then fully connected. That's one type of layer. There are many more different types in there, and you learn as you go about them. But the fully connected means really from, if I go back to the previous one, each neuron from the previous layer gets to all of the next one. As you can imagine, that gets pretty heavy pretty fast, but here it's okay. So we're using that. Give it a name, hid 1 for hidden, and hidden 2, and more dropout layer, and that's kind of where we put out. Network defined. All right, time for training. And my boys, I thought I'd give you a break at this point. It is a lot of input. But yeah, training, I mean, data acquisition, that's one part. And as I said, kind of we're just pulling down the prepared data. A lot of work has been done for us. So that's really good. Usually you would be very, very busy to get that to that point already. Okay. Import brainstorm. In the examples, if you actually look at their webpage, they import SBS. I thought, no, it's not really good. Not in an English-speaking country. Swiss might be okay with it. So I went with that. And you initialize it, and you just give it, Gaussian means kind of noise. You just set it's everything randomly, because you don't know where to start. So you just say, pick something. And then you initialize the trainer, brainstorm trainer class, and for training, you have different choices. Again, we are using a momentum stepper, and if you remember back to the 3D valley slide, you're the skier who wants to go downhill. That tells you how big your steps are. The bigger the learning rates, the bigger the jumps are. You're jumping more into the fog, and the momentum is like how much can you actually change direction. It's not suddenly, oh, actually, no, I'll go uphill again and turn around. How much can you let this happen? So you can influence how fast or how long your training is, because if you want a very precise, very small steps, it can take very long, costs a lot of resources, so it's just trade-off. And then I only mentioned here one. Once you have the trainer object, you add hooks. There are different hooks in here. That's a pretty neat one, and you'll see it in the next slide. It gives you a progress bar. So it actually tells you, when it's running through training, what is happening. And you get a little bit of a sense for that stuff. All right, we're running step 2 from our little example. So it starts to run, and then it says, hey, before training. And how accurate are we? Okay, randomly, 0.11%. Well, you have 10 things to choose from, so yeah, okay, pretty much random. It's what you would expect. And we have something in there, a hook. It saves actually the network into this file. That's locally, and it's again in the HDF5 file format. Makes it very efficient. All right, we leave it running, and every run, think of it as an epoch. And in there, you see 1, 2, 3, we have these mini batches. Always 100 samples, goes through, comes to the networks, and says, okay, my sample, I know it from classification, it's 3. Statistically, what comes out at the end is, okay, the likelihood for 0 is 10%, for 2 is 8%, and so on. It says, how well did that go? And then something is called backpropagation happens, where you say, okay, I actually know what the result is, I know what the outcome is, I have to adjust it. And it goes back and adjusts the weighting in the network. It gets better and better, and you're starting to fine-tune the weighting in your whole network. And you run. Next epoch goes through until I stopped it here after 10. Just to see how well that goes. And you see the accuracy is now at 95%. Not bad for 10 runs. And you see each run took about 30 seconds. That's not with the GPU, that's just running on this old notebook. So it's half decent. To get to a good result around the 98, 99%, you need around 100 epochs. I let it for 500 and I put it up into the repo, so even don't have to run the training. You can download it from GitHub if you want. And you can go straight to step 3. By the way, the best one, not with brainstorm, but there's actually shootout because this data set is so popular. It's currently 99.77. If you can do better, you should publish. The loss in the rolling training, which is up here, is with the dropouts and the stuff that didn't get into the adjustment. That's rolling, kind of, that's around kind of the every batch. and then you do it kind of with the validation the same. And that leads directly kind of to the next slide. Thank you very much, because you want to actually compare what happens when you train. Here's your accuracy. So the higher, the better. And you see down here the epochs kind of we're running through. Oh, it's pretty bad. It's getting better. It's getting better. And then starts to flatten out until, well, one day, well, you never will reach one, but getting close to it. But the validation isn't actually getting any better. It's actually with the unknown images. It doesn't hit it as well. And that's where the dropout, because the network learns so well the exact examples and tries to fit that exactly, that it's not actually getting good at kind of the unknowns. But we want to train the unknowns. And so by actually dropping some of the information, make it not it exactly, you're getting a much better result. You see kind of the validation actually as trumping the training, which overall, we didn't train it as much here. The curve is flatter. It takes longer to get better. But the validation is much better. And that's where the dropout layers become useful. And this noise where you think, like, it doesn't make sense, kind of throw 20% or 50% of your information away. But it actually works. And I also read that story that Kasparov was playing IBM, that IBM only actually won Deep Blue won because of a programming error, and Kasparov didn't expect the move. So actually noise is, in this scenario, is not bad, which amazed me when I came across it. With all this, putting it together, adjusting it, how many neurons on a layer, how many layers, the weighting, things like that, training data, preparing, and so on. The tools are there. And you'll find kind of there are many also very big frameworks out there, very full stuff, but still you're key in terms of how you put it together, how it works for you, and to actually be useful for your scenario. There's no universal architecture. I mean, that's kind of the holy grail. You won't find something that kind of learned anything. And also where you want to get away from the training, where you're saying, oh, all this training prep, can't it be self-learning? And genetic algorithms and things like that kind of are looked into in terms of like, okay, this could actually help. So it's not human-assisted. On the other hand, there is so much information around that is already classified and that can be used that you can base it on. So you might have to find the case there. So it's really down to you to find the right stuff. All right. That's the last one. And that's the whole code for actually classifying it. Let me step behind here. You see, we're just reading in network information from the pre-created file, and you reuse that over and over and over again. Also the reason why it works nicely on your smartphone, because all the hard work for speech recognition, stuff like that has been done, and you only read the trained information back in. You get your test image, do a bit of reshaping, run it through, and said, hey, what's coming out of it? Why is it not? Oh, sorry guys, I was only shifting it here. Can't actually see that. Sorry, I have it duplicated. Now I understand the blank looks. All right. No, I had that on the presenter screen actually all the way. Okay, no touching. Okay, and you run it through, and then you say, okay, what's the highest value in my classification? And I would be interested in actually see, okay, what did you think for, in this case, where is it, my number 3? right, 3 image, what was the likelihood, the percentage he gave for the other numbers. And that's what the output looks like. So recognized, yep, number 3 with 0.9999999, almost 1. So I'm super sure. 0, and don't ignore the minus 10, which means like here there's actually 10 zeros. So 0.0000000 blah. So it's very, very small there. So it's the algorithm is very sure it's a 3. And it's actually right. In the repo there are a couple of other ones. Well, I have to thank my family who was okay with me taking over the playroom with stuff where I constantly had to say, don't touch, it's not for you. My employer sent me here, Ministry for Primary Industries, and for you, you guys for showing up and showing interest, and you can catch me at the conference and we can chat a bit more. Thank you very much.
All right, we've got time for just maybe like 1 or 2 quick questions. So if anyone has any, okay.
Thank you for your talk. I was just wondering, there's a lot of neural network artificial intelligence frameworks available for Python. What or when would you recommend using brainstorm in particular, or what's the best thing about it compared to other things that are available?
The best thing is it's actually not too big. I mean, you can troll through the code base in a weekend and get familiar how it's set up. There's a lot of tooling in there. It is not necessarily kind of the one thing you want to put into production, and the documentation isn't great. I mean, there isn't too much on there. It's really literally read the code in many examples. But it's not so overwhelming as other big frameworks. And if you actually look at how somewhere I saw a list of how popular is what, it was like pretty much down at the bottom. But for me, it had the cute factor and enough tooling, enough stuff to actually experiment with it. What happens actually kind of if you don't use dropout layers? What happens if I use in my hidden layers only 50 neurons? And how does it explode and react? It has a little tool with it that actually also creates and designs networks for you. And some of the tips are kind of like in there, so you can still follow along kind of what's happening and what they thought kind of when they put it in there. Goes into that. That's the tool I mentioned, the create network from spec, where you come up with a specification with, oh yeah, I'm going to try that, and actually does it for you. And so it's not so error prone. You can obviously do it yourself, and you can even create your kind of like own layer types and whatnot. I mean, you can go completely crazy. Your own architecture, and that is not recommended. Don't do it by hand. You get it's insane.
All right, thank you. I lied. We only had time for one question, turns out. So can we just all thank Holger for his great talk?
Welcome.